Our last podcast today, last podcast of the semester, and we're going to end kind of on a bang, the Big Bang. We're going to talk about the origin of the universe. Where did the universe itself, the cosmology, the study of everything that is, where did it come from? So that's the concept, the conversation that we're going to have today. And so, pretty interesting concept. A lot of questions I'm sure you're going to have about this. Make sure that you're just writing those questions down and ask them of me in class so that we can kind of dialogue about this. It's really a big topic. So let's get at it. All right. It's the origin of the universe. The early universe is high temperature. Remember we talked about that there was this kind of small sort of primordial atom. And very high density imply that it may have had a very simple structure. So what was this tiny little primordial atom? What was it like? The thing that we talked about in the last podcast was the size of a pinhead, actually smaller than that. That's just so hard for me to wrap my mind around, that everything that is the stars and the planets and you and me was at a pin. Okay, that's weird. The mass and the radiation mingled in a manner unlike the sharp distinction today. Now what that means, if you look at the universe, okay, the universe consists of two things right now, if you will. Matter, like this pin right here is made of matter. Atoms, protons, neutrons, and electrons. I am made of matter. But there's also another thing that's going on that we don't think about oftentimes, that is energy. There's lots of energy in the universe as well. And we kind of think them as two separate things. But the thought is that at that primordial atom, they were mixed together as one thing. And so there was no big distinction between them. Radiation was so energetic that it easily transforms to mass, and mass and radiation behave as a single entity. This is related to the E equals mc squared equation. Okay, now we've talked about this quite some time ago. This is Einstein's equation. He said that the energy is equal to the mass times the speed of light squared. So you can change mass. I can take this pin and convert it into energy. Okay? And there would be a lot of energy in this. This mass times the speed of light, and then you square it. That's a huge amount of energy. That's the energy that's happening or being transformed in the center of suns, of the stars of the universe. That's nuclear fusion that we've talked about. Okay, but that's what's happening. There's the transformation, and the thought is that they can go back and forth. You can go from energy to mass and mass to energy. Okay. So they can be transformed into energy as in stars, but that energy can also be transformed into mass. It's kind of going back and forth, maybe like a double arrow. Okay, we can have energy on one side and mass or matter on the other side. It's going back and forth in this primordial atom. So the creation of mass, however, must come in pairs. Now this is a wild thought. I know that these are just hard podcasts to wrap your brain around. We must think of something called matter and then, well, antimatter. Now, there's a weird thought. What in the world is antimatter or an antiparticle? An antiparticle is, these are going to be some words you may not completely understand. There's a thing called a positron. The antiparticle of an electron is called a positron. The antiparticle of a proton is an antiproton. So there's actually, we've learned that the universe now consists, at least matter, of protons with a p positive, neutrons in zero charge, or electrons. But each of these has a counterpart, an antiproton, a positron for an electron, and the neutron has an antineutron, I think it's called, or whatever it is. Okay. And then so here's kind of what the scientists think about the whole Big Bang guy, okay? At 1 microsecond after the Big Bang, the temperature is 10 to the 13 Kelvin. Now that, my folks, is a lot of temperature. What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That is a very, very, very high temperature. Hot enough for protons to create a thing called quarks and antiquarks. Okay, there's the antiquark, which would be like an antimatter of a quark. What in the world's a quark? A quark is a piece of matter that is smaller than a proton. Okay? The diameter would be smaller than the Earth's orbit. So now that you say, well, that's pretty big, really. No. This is everything that is in this. All the stars are all compressed into this thing, everything. And then the universe begins to expand at roughly the speed of light, and then it gets cold. Because as something expands, it gets cold. You ever had a, like a CO2 cartridge. If you take a CO2 cartridge and then you let the gas escape really, really fast, it gets really, really cold. So when you expand a gas, it cools. And so now this is all gases because the temperature is so high that they can be anything but gases or particles. It's really a gas. And they're expanding. And as they expand, they cool. Okay, but we're such a high temperature, 10 trillion, I think it is, degrees Kelvin, 10 to the 13 Kelvin. It's just unbelievably hot. But it's going to start cooling. Okay. Now, we're at a lower temperature, so we don't make any more quarks or antiquarks. And so the physics of this dictates that the quarks annihilate, leaving an excess of quarks. And then the ones that remain, a lot of the quarks, when they combine, boom, that's energy and stuff, they just kind of annihilate each other. We have some quarks, and they combine to make protons and neutrons. All right, so we have this called this inflationary universe. So here's the primordial atom. This is the part we'd say we wonder, where did that come from? Nobody knows. No scientist has ever gone there. Okay, or they've gone there, but they've never figured out the answer. And after 5 seconds, it cools enough for the creation of matter to cease. So all the matter now is made. So you have lots of matter. At 3 minutes, you think, how in the world, this is my question, this is my question for you, see if you can ponder this, how in the world did they figure this out? Where'd they come up with 3 minutes and so many whoa! I mean, we've got the Big Bang down to seconds and minutes at the beginning. Again, this is all the math. They've done the math. It's all about the math of both the gravity and also the gravity, or the math of all the equations, of all the particles and antiparticles and atomic physics. So, all right, after 3 minutes, the temperature is now a few hundred million degrees, so it's cooled down a lot. And now a quarter of the protons fuse to helium. This is that thing we talked about in the last podcast where like 22% are helium, and we wouldn't expect that, but we would actually based upon this. So this theory kind of helps confirm the fact that the oldest stars have like 22% helium.